God, I have so many stupid tabs open. All right. All right. Let's get this started. I have about 30 tabs open. It's pretty dumb. I don't know why I do it to myself. But I read interesting Wikipedia articles. I'm like, I want to read that later. And then I don't. And it's forever stays open on my computer. Stupid. Where is this review? I know I have it. I know I have it open somewhere. All right. Problem 1. Problem number 1. How's everyone doing tonight? Not good. Some are good, some are shitty. Good to know. Problem 1 says, use a suitable change variable. I think I gave mic privileges to Dr. Professor Williamson, so I think that's the other microphone you might be hearing. Dr. Williamson, thank you for joining us. Would you like to say something? You're the only other microphone I've activated, so... Okay, I'm just going to take away your mic privileges then. You're just going to sit there in the corner and not say anything. Alright, problem 1. Use a suitable change of variables to evaluate the triple integral, double integral z dv, where the solid E is bounded by the elliptic paraboloid z equals 1 minus x squared over 4 minus y squared over 36. What you'll want to do here is use the substitution x equals, let's use a different size font. By the way, apparently, Laura, I'm going to try and not make this longer than 2 hours. I want to be out of here by 1:30. I want to make last call at the bar, so I'm going to try to get out of here fast. X equals 2r. Oh, okay, this mouse is, hold on. I got to close a few tabs because I can't quite draw right now. So give me a second. R cosine theta. I'm going to try and do as much of the review as possible. 2r cosine theta x or y equals 6r sine theta. Now with this transformation, you need to not only compute the Jacobian, but also the bounds when you do this. So let's find the Jacobian. The Jacobian is going to be, what's the partial derivative of x with respect to r? That's going to be 2 cosine theta. What's the partial derivative of y with respect to theta? That's going to be 6 sine theta. Now we take the derivative with respect to theta. That's going to be negative 2 r sine theta. And the derivative of 6r sine theta with respect to theta would be 6r cosine theta. Alright, taking the determinant of this to get our Jacobian gives us 12. Basically, if you do 12r, because you have 12r cosine squared plus 12r sine squared, but 12r so cosine squared plus 12r sine squared is just going to come out to be 12r. Cool, so that's your Jacobian. Keep in mind, don't confuse this with RU cross RV. A lot of people are telling me, oh, how do I get RU cross RV for this? This is not RU cross RV. This is Jacobian. And in fact, in my review, I might have mentioned that RU cross RV acts like a sort of Jacobian, but I wouldn't treat it like a Jacobian. If you keep doing that, you confuse the two. So don't think of RU cross RV as being a Jacobian. It acts like a Jacobian, but don't think of it as one. I'm sure Professor Williamson also mentioned it during lecture. Okay, so that's our Jacobian. This transforms the region z equal, or the curve z equals 1 minus x squared over 4 minus y squared over 36 into 1 minus r squared. That's what happens when you plug this in for x and this in for y. Yes, Thomas, RU cross RV should be reserved for surface integrals. Z equals 1 minus r squared. All right. We're going to be doing the triple integral of z. Well, I guess to be fair, I probably should have also included the z transformation, but the z transformation doesn't take into consideration much either. So z is still z, so z equals z. Yeah, team no sleep. You're kind of right because you're saying it's a triple integral, so we're supposed to do a 3×3 Jacobian. We don't do a Jacobian because it's a triple integral. We do a Jacobian because we need to use a change of variables in order to transform 1 minus x squared over 4 minus y squared over 36 into something that's a little more reasonable. So z equals z is something is going to be part of our transformation as well, but still the Jacobian is 12r. So our triple integral becomes z, and as we found out, our Jacobian was 12r dr d theta. 12r dz dr d theta. No, Alex, it's not just r dr d theta. This is because we're using 2r cosine and 6r sine. That's not our standard. That's not our standard polar transformation. Standard polar would be x equals r cosine, y equals r sine, but this is x equals 2r cosine and y equals 6r cosine. You have to compute the Jacobian for that. So z times 12r dz dr d theta. If I integrate, oh, now we have figured our bounds. That's the next thing. What are our bounds going to be in terms of for z? Well, let's kind of get a quick sketch. That's the phrase that I say that you guys dread the most. Let's get a quick sketch. Yeah, that pisses you guys off, I'm sure. So here's the paraboloid. The bounds for z. What we're going to do is we're going to draw a line from below the region up the parallel to the z-axis. What do we hit first as we enter the region? We hit a lower bound of z equals 0. As we continue through the region, we hit z equals 1 minus x squared over 4 minus y squared over 36. But as we transform that into 1 minus r squared. So that's our upper bound for z, 1 minus r squared. Our bounds for r. Well, ask yourself, for what value of r is 1 minus r squared equal to 0? You should tell me that's true for r equals 1, or negative 1, but again, we don't take r to be negative. So r goes from 0 to 1. Lastly, theta is, it seems that we're going to go all the way around this elliptic paraboloid. There's nothing restricting us from being in the first octant, so theta goes from 0 to 2 pi. Integrate that guy, and you'll be fine. That's your answer. All right, so let me answer some of the questions we have here. Morgan says, can it go from 0 to 1 minus r squared? I think you did. I guess you asked that after or before I got it up there. Bridget asked a good question. How do I know to do 2r cosine theta? Bridget, look at z. Z is equal to 1 minus x squared over 4 minus y squared over 36. Look at the coefficients of x squared and y squared. They're not the same, so it's not quite a circle. It's actually the intersection that z has with the xy plane is an ellipse, and I tried to draw it as such. Can you kind of see that elliptical shape that we have that this makes with the xy plane? As a result, I can't just use your standard polar conversion. I need to make sure I choose a suitable coefficient for cosine theta and a suitable coefficient for sine theta so that it cancels the 4 and it cancels the 36 in my denominator. Can we not do simple integration to save time? Yeah, sure. I'm not going to bother wasting my time doing this integral. I know you guys could do it. Save it for the art integrals. Good point, Nicole. I don't understand why the bounds are the way they are. Shouldn't r be the one that varies since the max value of z is 1? No, we're kind of doing cylindrical coordinates here, right? You see dz, dr, d theta. So because dz is first, I ask myself as I draw a line parallel to the z-axis, what do I hit first? As I enter the region, I hit the plane z equals 0. That's this ellipse down here. So that's my lower bound, 0. What do I hit as I leave the region? Well, I hit the equation 1 minus x squared over 4 minus y squared over 36. Well, that in terms of the coordinate substitution that I use is the same thing as 1 minus r squared. I think that's about it. Okay, we're going to move on to problem 2. We can come back. I can answer questions about that a little bit later, but for now I'm going to move on. I'm going to try and make this a little quick because people say they got to go. I'm going to try and make last call, but we'll see. Find the area of the region in the first quadrant bounded by the asteroid. Square root of x over a plus square root of y over b equals 1 and the coordinate axes. Okay? Square root of x over a plus square root of y over b equals 1. There's a multitude of different substitutions you can make in order to make this work well. You can use x. What I want to use is x equals a r cosine to the 4th of theta. A lot of people are going to wonder, why did you use cosine to the 4th? Oh, hold on. Let me get this first. All right. So the reason we're using sine of the fourth and cosine of the fourth is because we want to abuse the Pythagorean identity. We want to use that cosine squared plus sine squared equals 1. Currently, on the power on x and y, we have. Don't ask me questions yet. Shut up, Morgan. Sorry. Right now, we're going to say cosine of the fourth and sine of the fourth. When we take their square roots, give us the cosine squared and the sine squared that we want. Sorry, Morgan. The a and the b will cancel. Don't worry about the r. We're actually not going to worry too much about the r right now. You can if you want to. You can if you so choose to put powers of 4 on the r if you'd like, but it's not necessary. So if we plug everything in, this gives us square root of a. The a's cancel, so I have r cosine to the fourth of theta plus square root of r sine to the fourth theta equals 1. So this basically becomes square root of r equals 1 because cosine of the fourth becomes cosine squared. Square root of sine of the fourth becomes sine squared. So we have cosine squared plus sine squared is 1. So this gives us square root of r equals 1. This tells us my bounds for r go from 0 to 1. Keep in mind that it tells us, it says first quadrant. So it wants the asteroid in the first quadrant. So that's going to be theta goes from 0 to 2 pi, or pi over 2. Oops. So now, I'm going to ask you guys a question. So stop typing for a second. First question is, the only question that really matters here, how do you find the area, or what do you compute the double integral of if you want to find the area of a region? Pup 11 is the only one that got it wrong. Steven got it wrong too. 9, for whatever reason, 9 came out of nowhere. 1 factorial, swag, Jacobian. Okay, we get it. Stop spamming. B, I'm going to kick you out. All right. Integral. We're not going to give him the boot just yet. Okay, so we're going to do the double integral of 1 dA. Well, what's our dA would be in terms of r and theta, but we need our Jacobian. So we have to go about computing a Jacobian. Let's kind of move this out of the way. The Jacobian for this, and this is where it's going to maybe take up some room. What's the derivative of x with respect to r? That would be a cosine to the fourth theta. The derivative of y with respect to r would be b sine to the fourth theta. The derivative of x now with respect to theta would be, shit, here we go, 4, it's going to end up being negative 4 ar cosine cubed theta sine theta. Sorry, it's going to be ugly. This term, I'm just going to put an arrow here. The term that goes here will be positive 4 b r sine cubed theta cosine theta. Okay, she gives formulas for the Jacobian, so you don't have to compute it. You can use the formula. I was not aware that she gave you a formula. You didn't think I knew that she was going to give you a formula? Do you think she's that nice? No, I didn't think she was going to be that nice. So, you can use the formula. Yeah, sure. With whatever formula that gives you, when you compute this Jacobian, you end up getting... This Jacobian ends up coming out to be... let's see, let me do this really quick. 4ab r... sine cubed. It's gonna, I think, a sine cubed cosine cubed. Something like this, yeah? dr d theta. And again, the bounds for r go from 0 to 1. The bounds for theta go from 0 to pi over 2. Alec, this is number 2. All right. So, Nicole, since you are the voice of reason here as far as this is concerned with what constitutes a difficult integral, do you think this is a difficult integral? Should I do this integral out? Can you guys handle this? Okay, I'm not going to do this integral. I think you guys can handle it. Let's actually pull up I like pulling up this poll pod, so let's do it. Add new poll. Should Andrew waste his time with this integral? Okay, that's a leading question. Should Andrew do this integral out? Yes. Damn it. Or no. Do this integral out. Very good grammar. We're going to go with a simple majority here. All right, I feel bad for the 37% of you who don't know how to do it. I'm going to give you a quick hint. Here's what you should do. I'm not going to do the integral. I'm just going to give them a hint. The powers on sine and cosine are odd. So you can use the substitution. U equals sine theta. Du equals cosine theta. Good luck. You can handle it. All right? Moving on to problem 3. All right, let's see. Problem 3, evaluate the triple integral of x dv where e is bounded by the planes. Let's tell you what, I'm going to try and direct you guys to the wall as much as possible if I feel like a sufficient solution's been worked out for that problem. So let me pull up the study edge wall so that I can point you to whatever post number it is where I think Nicole actually already worked a problem like this out. Hold on. Nicole and I worked something like this out. A lot of people already did, actually. So let me search this post. 1 second. (20528). Yeah, 20528. Thanks, Alex. Post 20528. For number 3, check out post 20528. Cool? All right. Moving on to number 4. Find the centroid of the plate bounded by the cardioid r equals a times 1 plus cosine theta. Okay, we might have already worked this one out on the wall, but I do have a few questions about it. Or a few points that I want to make about it. So first off, I want you to find the centroid, xc comma yc. Apparently that when she says centroid, it's understood to have a homogeneous mass. So first of all, we need to find the mass. So the mass of this centroid, or the mass of this cardioid, we're going to have to do the double integral of the density function. The density function is understood to be 1. So we have 1 dA, but because we're doing polar coordinates, this is going to be the double integral of r dr d theta. Our bounds, actually, this is one thing you have to be really careful about, and I'm pretty sure that if you do it from 0 to 2 pi, you get the wrong answer. You actually end up with 0 for the x component. You get up 0 for the mass. That doesn't make sense. So be very careful about this. Maybe not. You don't have to. Let's just do 0 to 1. This is a times 1 plus cosine theta. And then our bounds for theta go from 0 to 2 pi. Okay, I didn't know. You always have to be careful, and this is just something I always keep in mind, that whenever I do a polar integral, I'm always worried that when I integrate over the bounds from 0 to 2 pi, one of the signs of the cosines is going to pop out and give me a 0, and that doesn't make any sense in terms of the question. You should never get a 0 mass. So keep that in mind, is that sometimes you might want to integrate over half the bounds and then double your answer, something like that. Cool? So if you do this integral, you get the integral of r dr is r squared over 2. Plug in a times 1 plus cosine theta. So let's flip the upper bound here. I'm actually going to drag this upper bound over. There's my upper bound. There's my lower bound. If I plug that in, this gives me a squared plus 2a squared cosine theta plus a squared cosine squared theta over 2. Okay? No. Where am I? Yes, over 2. Okay, now. Someone said, I thought the mass had density somewhere. Yes, Morgan, you're right. But because this is understood to be, they didn't give you, they said the word centroid. So the word centroid tells us that sigma equals 1. We're just going to say that sigma equals 1. Cool? All right, now we have to integrate this from 0 to 2 pi. And if you do this with respect to theta, this gives you a squared over 2 theta. Shit, I'm going to run out of room, but let's get rid of this. This can go. I'm just getting the mass first, and I know this is probably an integral you guys probably don't need me to do, but a squared over 2 theta plus a squared sine theta. And again, this is just because I wanted to do this out for my own peace of mind and because I had a few things to say about it. The integral of a squared over 2, let's pull the a squared over 2 out. So a squared over 2. The integral of cosine squared is theta over 2 plus sine squared theta, 2 theta, oops, oh, sine squared, sine 2 theta, I'll lose my mind, over 4. And then again, evaluate from 0 to 2 pi. Now, when you plug in 2 pi and you plug in 0, you get, let's see, what do you get? What? 3 pi a squared all over 2. That ends up being your mass. Do I have a minus? What? I don't think I have a minus somewhere. I don't think I should have a minus. Yeah, someone takes a shot, not me. Okay. But I guess for Professor Williamson, taking a shot is not a big deal. All right. So we've got the integral. That's our mass. Shane, I believe it's being recorded. We have Ryan who's recording. I don't know if he's got the audio recording, but whatever. It's not a big deal. I mean, I'm sure that anybody who watches a third-party recording, yeah, everyone stop and thank Ryan for being a sport and recording it. Hopefully it's not like a super massive file because we all think, I'm thinking a screen capture of a 2-hour session like this might take up 5 gigs, but who knows. Ryan, thanks, you're the man. I'm assuming, Mr. Smith, how did I get theta over 2, sine 2 theta over 4? Are you really asking me that? Okay, the answer is, it's the half-angle formula. The half-angle formula. You got to know the half-angle formula. All right, not a problem. Just remember, we've talked about it before. The integral of cosine squared theta equals theta over 2 plus sine 2 theta over 4. You remember that. I know you do. Okay, so that's the mass. Now, the next part is a little bit harder because we do the double integral again, but because we want the x-coordinate of the center of mass, we need to say x times dA, or x times r dr d theta. Now we have to make sure to convert x into polar coordinates, so that means we transform the x into r cosine theta, thus giving us r squared cosine theta dr d theta. The bounds are still the same. The bounds never change. Actually, that's something to keep in mind. Your bounds won't change when you compute the x-coordinate or the y-coordinate as you move from the mass to the double integral. I don't know. I might be going through every single question, but I don't know. All right, so the upper bounds are still a times 1 plus cosine theta. Now, I've got something to say about this. The integral of r squared is r cubed over 3, and if you plug in a times 1 plus cosine theta, that's going to give you a cubed times 1 plus 3 cosine theta plus 3 cosine squared theta plus cosine cubed theta. This is all over 3. And then don't forget, there's actually this cosine sitting on the very right saying, hey, I want to party. This cosine's still here. So we actually have an extra cosine theta. And we would be expected to integrate that with respect to theta from 0 to 2 pi. So I know you're panicking. Morgan, yes, she probably won't give you something this bad on the test. I want to give you a few tricks that you can use. Again, cosine of the fourth isn't something I wish on my worst enemy to try and integrate. It takes some time to do. At the very least, you can take this to the bank. Cosine cubed theta d theta, the integral from 0 to 2 pi will be 0. Actually, for that matter, cosine to any odd power. Cosine to any odd power. Cosine to any odd power from 0 to 2 pi, the integral from 0 to 2 pi of cosine to any odd power will be 0. So that allows you to get rid of, well, you're looking at cosine squared, but when I multiply this cosine in, it's going to be a cosine cubed, so that go away. This will go away, but I'll still have to integrate what will eventually become a cosine squared and a cosine to the fourth. I mean, still, icky. Again, this is why you use Wolfram alpha for this question, because Wolfram alpha will save you time integrating this function with respect to theta. That's all I have to say about this question. One other thing she'll say is, usually for a bonus on this type of question, she'll say, why can I be sure that y, really quickly, how do I know that yc is 0? How do I know that y sub c is 0? I don't know. Well, it's because the cardioid, this is what r equals 1 plus cosine looks like. The cardioid is symmetric over the x-axis. Moreover, the density function that we've been given, sigma equals 1, is also symmetric about the x-axis because it's a constant. So we should expect the y-coordinate of the center of mass to sit somewhere on the x-axis. There is just as much mass above the x-axis as there is below the x-axis. So because we see as much mass above as we see below, the y-coordinate should be 0. All right, so now that I've said that, let's see what... You have to give Ryan money. No. Should we? She won't give us something like this on the test. No. Lindsay says, oh gosh, damn it, I haven't decided yet. Yes, I will. I am late dead. Professor Williamson can stroke my leftical. Hey guys, icky, ooh, do you have to take a shot? Why do I take a shot? Did I make a mistake? It's true, clothes looks like a butt. Yes, it does look like a butt. Actually, this is what Calc 2 is doing tonight. We were going over, I said, okay, I said, so it's called a cardioid because, you know, 1 plus sine theta kind of looks like a heart. And you might say, okay, well, 1 minus sine theta doesn't look much like a heart. I mean, that looks like a 5-year-old drew it, or maybe Michael J. Fox drew it. And everybody goes, oh, that's upsetting. Michael J. Fox, I can't make Michael J. Fox joke? No, Parkinson's jokes are offensive. Okay, so, sorry. I thought it's hilarious. All right, so, moving on. Henrik, you said, why do I have to solve for theta? Okay, fine. You guys can hate me for the Michael J. Fox joke. Jesus Christ. 0 to 2 pi, it's because the cardio doesn't actually touch nowhere does it touch the origin other than pi, I guess, but it still continues to trace out. Good, I'm glad that at least 2 people thought it was funny. All right, moving on to problem number 4. Let me pull it up. Problem 5. Find the center of mass of the part of the ball x squared plus y squared plus z squared less or equal to 4 that lies above the cone z squared to 3. Okay, I'm going to rewrite this as z equals 1 divided by square root of 3 times the square root of 3x squared plus y squared. By the way, this is the cone. Phi equals pi over 3. You should know this. Oh, shit. Pi over 3. All right? Yeah, this is number 5. So, we first got to find the mass. Okay, that's unfortunate. The mass, and this is the mass of the whole thing. This is the mass of the solid. Listen up. It says the mass of the solid. Or does it say the solid? No, I guess it doesn't fucking say solid. Cool. It doesn't say solid, so nothing here conveys to you that we should be looking at a 3 integral, but if you see the word solid, or you see volume, or you see spatial region, you should be thinking triple integral. If you see plate, or you see the word plate, or planar curve, or lamina is also a word that's sometimes used. Lamina, it's a nice word. Lamina. Lamina is just another nice word for the word plate, though I don't know if that word, you've ever seen that word before. Yes, lamina. It doesn't happen often, but if you see it, it just means plate. It'd be a double integral or a double integral. And if you see wire, if you see the word wire or curve, that would be a single integral. Okay. So don't worry, lamina, not a big deal, not a big deal. All right. So again, I'm just giving you words. I'm just trying to give you all different languages of words that could possibly be on that exam. All right. Triple integral of the mass. To find the mass, we're just gonna do sigma dv. Well, sigma, we've been told that the mass is proportional, so k. We need a k because it's proportional. Okay, God. Triple integral is usually, I'm going to type this out, is usually conveyed, triple integral for mass, I should say, is usually conveyed by the words solid, spatial region, volume. That's about it. Double integral for mass is usually lamina, plate, planar curve. That's about it. Stephen, it says proportional. So because it says proportional, we need a K. Single integral for mass is usually curve or wire, or you'll see linear density. These are some keywords here. So K, we see the word K. That's because we said proportional. At least I could be completely wrong, but I could have sworn it said proportional, in which case I'm very sorry. Proportional to the distance. We need a K. Proportional to the distance. The distance from the origin to a given point would be square root of x squared plus y squared plus z squared. But because we're probably going to be doing spherical coordinates for something like this, we're probably going to want to do, we're going to convert x squared plus y squared plus z squared into polar coordinates. Well, x squared plus y squared plus z squared is rho squared. So if I replace that by rho squared and take the square root, I get double integral of k then rho, k times rho. Moreover, dv, the Jacobian for spherical coordinates, is rho squared sine phi. d rho, d phi, d theta. Now, what are the bounds for this integral? Let's see. What's the radius of the ball? Damn. Okay. I'll get that later. I'll get your question later, Thomas. That's just the square root of x squared plus y squared plus z squared is the distance from the origin to any given point. Okay, what's the... Okay. Balls was not an appropriate answer. I can tolerate a little bit, but let's put it this way. Can anyone tell me what the shape of Italy looks like? What's the shape of Italy look like? A boot! That's what Kim Jong-un is getting. The boot. See ya, Kim Jong-un. Alright. Also, penis. Gollum, you're gone. You're getting the boot as well. Alright. The boot. Alright, so. I know you just refresh and come back. That's probably what's going to happen, but whatever. K rho times rho squared sine phi d rho d theta. D phi d theta. The thing is, we need to integrate this over what bounds for rho? 0 to 2. A lot of you said 0 to 2. How about phi? Well, it says above the cone, so we should be going from 0 to pi over 3. And then we want the entire region, or there's nothing restricting the first octant or anything like that. So 0 to 2 pi. So those are our bounds. This is only going to give us our mass. Now, what might be unnerving to some of you is that you have to do this all over again, but for x, y, and z components. But I can at least save you some time for the for those components because let's draw the region really quickly. Draw a different color. The region we have is symmetric around the region we have here, the ice cream cone region that we have is symmetric over the x and y axes. Moreover, the density function we were looking at, sigma equals square root of x squared plus y squared plus z squared, is also symmetric over the x-axis and over the y-axis. You can do this because when you replace x by negative x and y by negative y, you get the same density function. Cool? So, because the density function and the region that we're integrating over are symmetric symmetric over the x and y axis, the x coordinate center of mass is 0, the y coordinate center of mass is 0. So I don't need to waste my time setting up those integrals. However, the z coordinate I do need to set up, so I need to start with 1 over mass. Why does rho start at 0? It has to. I don't know how else to explain to you other than that's where the radius starts. Like, tell you what. I'll let you tell me where you think it should start, and then see if it makes. We'll see if it makes sense. 1 over mass times the triple integral of z times, and then times our rho times rho squared sine phi. Remember that you need to know your spherical coordinates. This z is equal to rho cosine phi. So that gives us rho to the 4th sine phi cosine phi. And then we'll do the triple integral of that over the same bounds. Any questions on that? Oh, there should be a k. Yes, Ben, there should be a k here. But again, those k's will cancel out. It's almost as if they weren't there to begin with, so it seems kind of silly to write the k. I've heard from a particular Alex who said their TA would take off if you didn't include that k. A point, I imagine, probably not much, but don't forget the k if they say the word proportional. It's annoying because it just cancels out anyway, so who knows. But the k's will always cancel out. At least when you find the center of mass. Cool? Moving on to question 6. I did question 6. I did question 6 in a video. Fuck you guys. Moving on. Number 7. Number 7. Find the mass of the helix r of t equals a cosine t, a sine t, bt. Okay. So r of t equals... Yes, number 6 is in a video, along with number 12. It's in a supplement. Check it out. Okay, this problem is not on the Facebook wall, and this one I can imagine gives a lot of people some trouble. So 1 over, or let's put it this way, we'll find the magnitude. So r of t, the magnitude, is equal to the square root of a squared plus b squared t squared. The density, we're told, is equal to the square of this. So the density function is a squared plus b squared t squared. Sorry, 1 over this. Sorry, it's going to be 1 over this. So this is our density function. So in order to find the mass of this helix, we're going to do the single integral. And again, why do I know to do single integral here? Why not a double integral or a triple integral? Well, the key word here is linear mass density. Linear mass density. So it's telling us just a single integral. Single integral of my density function is 1 over a squared plus b squared t squared. I did. Whoops. I will fix the switch in the sine and cosine. My bad. Actually, we're going to pretend like it doesn't matter, because it really doesn't. Okay. The dt, or your d, remember, you should be doing ds here. Well, my ds, let's compute that really quickly. Larissa, why is it 1 over blah blah? You should know. You're the professor. So ds is equal to, square root of ds dxt plus dy dt squared, yada yada. That's just I'm gonna save you some time. That's just gonna come out to be a squared plus b squared. Maybe you should change your name to something other than Larissa Williamson. I know it's funny, but I want to know who you are. Not just because, I don't know, Larissa Williamson. There's 3 Larissa Williamsons in here, and I lose track. Square root of a squared plus b squared dt. So I'm going to replace ds by that. Let's just put this, let's erase this guy and move him here. And now I feel like I'm missing one small thing, but I guess I'm good. We're integrating over 1 full turn, so 0 to 2 pi. All right. So now the question is, how the fuck do I integrate this, all right? Step 1, factor out the square root of a squared plus b squared. And we're also going to factor out something you might not have expected us to factor out. We're going to be factoring out a b squared from the denominator. I'm going to factor out a b squared from the denominator, so watch carefully. Factor in a b squared from the denominator, and the square root of a squared plus b squared gives me square root of a squared plus b squared. Yes, Thomas, don't spoil it for everybody. We all know it's going to be, okay, maybe not. But yeah, Thomas, you're right. It's going to be arctangent. This gives me interval still 0 to 2 pi. How do I know 0 to 2 pi? I swear to God, if it's in the bounds, if they told me. Oh, sorry. That's my fault. Not 0 to 2 pi. It is a to b. When I think helix, I always think one turn is going to be 0 to 2 pi, but they did say a to b, so that was my bad. A over b, was it a over b or b over a? A over b. A over b. A over b. All right. My bad. Okay, so what do we have left after I factor out the square of a squared plus b squared and the b squared from the denominator? This gives me 1 over a squared over b squared plus t squared. This is weird because you probably don't You might not know. Yes, I earned myself a shot with that one. We'll get drunk. I think Study Edge is actually gonna have a party. I don't know how many of you are over 21, but there's supposed to be some sort of I don't know. We usually do like end of the semester party. Perfect time to have a party, right? And we just do it, throw it at Midtown, and I don't know, close the bar down and have a Study Edge party. Yeah, I'm serious. With a bar tab. And we're doing it now, especially because I think the Study Edge fan page recently hit. I think it's Cafe Risque. But you can call it Club Risque to make it sound like you're not a frequenter, but it is Cafe Risque. Yes. Oh yeah. Oh, my mistake. It was Club Risque. Oh, Cafe Risque. I mean, I wouldn't know. I don't go there very much. Yeah, I'm sure you do. Okay, just kidding. Yeah, you work by there. You sure you don't work in there? All right. So, no, yeah, we usually like close down Envy or whatever. I think last year was last semester we did Fat Daddies or something, and we had a bar tab there. So 1 over a squared. Yeah, the English major's back. Actually, I'm pretty happy about that. Nice. He was pretty cool. 1 over a squared over b squared plus t squared. The integral of this guy, I probably should move on. This is arctangent. This is an arctangent integral. Thomas said something to that effect. So the integral of this guy, not counting the well, just might as well put this out here. A squared plus b squared. Actually, I don't know for him to do it there. Square root of a squared plus b squared over b squared. When I integrate 1 over a squared over b squared plus t squared, I get times b over a arctan of bt over a. Yes, Boba Fett's got it. Right there. 1 over a arctangent of x over a is a secret formula. A and b replace x and y respectively. No. A and b are constants. Okay. We good? This is an arctan integral. Boba Fett CPA told you to use what I like to call the arctanwich, or he said the secret formula. If you want to write this one down, I recommend you do. This is the integral of 1 over a squared plus x squared dx is 1 over a arctangent of x over a. You need to know this integral in order to do this problem. Otherwise, Wolfram Alpha has to do it for you. This is what I like to call the arctanwich, because there's an arctanwich in the middle. Cool? That's how you do this problem. And then you plug in, okay, so let's go back actually. Shit. Boom. Oops, whoa. Plug in a over b, plug in 0, find the difference. When you do so, arctangent, because we have arctangent of 1, which would be pi over 4. The b cancels with one of the b's down there, and you get pi square root of a squared plus b squared over the 4. There's an a there. There's an extra b in the denominator, 4ab, and I believe that's the answer. Cool? Why not b squared over a squared in front of the arctangent? It's just b over a. The formula says 1 over a. If your formula is 1 over, this is for the integral of 1 over x squared plus a squared, you only take the square root of your a squared to get just your a. You take the square root of a squared plus a squared over b squared, which is just a over b. Flip it and that gives you b over a. Pay attention to the square. It's really important. Okay, answering questions now about that problem. Where does the pi come from? Let me answer that one like this. All right. One more time. Square root of a squared plus b squared. We had a b squared in the denominator. The arctan integral gave us b over a. Arctan of a over b. I'm going to move on, I swear, really quickly after this. bt, I know some of you are pissed. Okay. Plug in a over b, plug in 0, find the difference. When you plug in a over b, you get pi over 4. When you plug in 0, you get 0. So you just get pi over 4. So pi over 4 times b over a times square root of a squared plus b squared over b squared. Cool. Moving on to the next problem. We're gonna have to ask your question on the wall for that one because I was tired of talking about that one. Moving on to problem 8. Evaluate the square root of 2y squared plus z squared. I believe we talked about this one quite a bit on the wall, so let me find out what question that was on the wall, and I can direct you to that question. I might as well do it. Shit. Okay, so here's the thing. There's lots of different parameterizations for this intersection. We have y equals x and x squared plus, I just want everyone to shut up for a second. X squared plus y squared plus z squared equals a squared. Equals a squared. So y equals x is the plane that comes through like this. I'll draw a bit better, I think. It's that plane right there. It extends forever in every direction. No, I don't mean sine for y. Listen, just shut up, just shut up, just shut up, just shut up and listen. Just shut your mouth and listen. Shut the fuck up and listen. I do mean this. You could also use a sine t and a sine t here. But what's important is that because you want to be on the plane y equals x, you must use whatever you choose for x. You must also choose for y because y equals x. All right? You can use a sine t, or you can use a cosine t, a cosine t. But whatever you choose, it's got to be the same. Now, whatever you get, you then plug in to the equation of the sphere. So I'm going to use the a cosine t because that's what I chose here. A lot of people were confused or thinking like, well, Andrew, didn't you use a sine t earlier? If you've seen me do this problem before, you said, wait, Andrew, didn't you use a sine t on the wall? Sure, I did, and it doesn't matter. I mean, I've told you that I say this in my review every single time is that there's lots of different parameterizations for the same curve. A cosine t, I can parameterize a circle in an infinite number of different ways. To be fair, I should be consistent, but I want to show you that there's no one way to parameterize a curve. There's some better ways than others, but this one actually has got a tie. We've got a few different ways we can do it. A cosine t and a cosine t for x and y will work. If I take a cosine t and plug them in for x and y, I get a squared cosine squared t plus a squared cosine squared t plus z squared equals a squared. All right, so right now, it's not looking good for us because if I rewrite this to have z squared and I subtract the a squared cosine squared over, I get a squared minus 2a squared cosine squared t. It looks good, but it could be better. We would prefer that instead, I mean, look, it would be perfect if that coefficient of 2 weren't there. If that coefficient of 2 weren't there, we would have a really nice parameterization for z, namely that z would equal a sine t. So here's what we're going to do. I'm going to take my original parameterization, and I'm going to divide this by square root of 2. I'm going to divide this by square root of 2. So what happens when I square both of those guys, by plugging them into the equation of my sphere, I get a squared cosine squared t over 2, a squared cosine squared t over 2. Together, those make a squared cosine t. So this 2 drops out. In fact, I'm just going to put an x right through it. This 2 will drop out, and I'll just have a squared minus a squared cosine squared t, which means that all this work gives me z equals a sine t, which is really nice. It's really nice to have this, just a perfect a sine t. Cool? Okay, Mother Williamson asks a question, so are the students just supposed to be able to recognize that? Let me put it this way. if I ask you, I think on the question, someone asked on the wall, someone asked, what, I answered this question by saying, think about what the y equals x in the plane, or the sphere x squared plus y squared plus z squared equals a squared looks like. We're talking about a plane and a sphere. And I think the analogy I used on the wall was envision a basketball and envision a guillotine. Suppose you situated that basketball right on the guillotine where you're supposed to put your neck, and you chop off Robespierre's head, or Marie Antoinette, or King Louis XVI, or whatever. And you put the basketball on that guillotine, and you take the guillotine, you let it come down. The guillotine's going to slice that basketball into 2 equal halves, and the cross-section you're going to see is a circle. As the English major said, what's a guillotine? No, he said it creates a circle. Yes, it creates a circle, and that's the important part here. It creates a circle whose parameterization doesn't quite look like, I mean, doesn't quite look like a normal parameterization for a circle, but, damn, you know history too? I do. Or I guess English major does too. It's a parameterization for a circle. It's a little weird because we had to throw in that extra factor of square root of 2, but we tinkered with it a little bit, and we got a parameterization that worked. Cool? All right, so now that we have a parameterization, the next step is to actually do the goddamn problem. This is a line integral, so we've got our parameterization. At this point, I think it's just a matter of subbing in. Step 1's done. Bounds, yes, good. Thank you for keeping me straight on my bounds, Bradley. 0 to 2 pi. For those of you who said, Andrew, didn't you use 0 to pi? I did, and I said I'm going to double my result because I didn't want you to think phi could go from 0 to 2 pi. But again, if you want to use the spherical way I did it before, using a sine phi over square root of 2, a sine phi over square root of 2, and a cosine phi, you can. Your bounds for phi will go from 0 to pi, and then you'll double your result. Here, I'm using a different method than I've taught you before, so if you haven't seen me do this problem, this is all actually just fine. If you saw me do the spherical way before, it might look a little weird. My bounds will be 0 to 2 pi, so I trust you guys can plug this in. 0 to 2 pi, this becomes square root of, when you plug this in, the 2y squared plus z squared, this becomes just a. Your ds, I believe, just becomes a. If you compute the square root of the derivative of x with respect to t, the derivative of y with respect to t, the derivative of z with respect to t, square them all, add them up together, take the square root. That gives you also a. So you're just doing the integral of a squared dt from 0 to 2 pi, and that gives you 2 pi a squared. Good? All right, we're done with that problem. Problem 9. Find the length of the catenary. So this is where she uses that hyperbolic sine and hyperbolic sinh. I'm going to write some formulas down because you should know them, because has she put this on her test before? Has she ever put any one of these questions on her test before? Okay, well, apparently she hasn't been doing it. Professor Williams says, if I hadn't realized that I had to divide by square root of 2, then would I be fucked? Well, conceivably, you're the professor, so you should know how to do it. But, yeah, I think so. I think you'd be fucked. Yes. But I think realizing to divide by square root of 2, I mean, you gotta use a little bit of ingenuity here. I mean, I'm trying to, as your study expert and kind of as your coach and as your friend, I'm trying to eliminate as much of the ingenuity and creatively thinking bit. I'm trying to take as much creative thinking out of the process for you guys as possible. I'm trying to reduce that to as small percentage as possible. This is where that 5% of you having to have some creative thinking about having to divide by the square root of 2 would come into play. So unfortunately, I don't have any sort of taking out. I kind of have to. That's kind of on you to do. Lastly, the derivative of cosh is sinh, and the derivative, okay, my browser's freaking out. Derivative of sinh is cosh. For those of you who actually use your actual first name, even if it's not your entire first and last name, I don't care, it doesn't have to be your first and last name, thanks. appreciate it. I guess the English major's okay, and the original Larissa Williamson, I don't know whoever does that, because everybody does it, so I can't really know. But CFITS, English major, the original Larissa Williamson, whoever that first was, I like them. They're fine. But, okay, keep going. All right. We're using these formulas, write them down. So for this problem, we want to find the length, which is weird. I don't know why she's asking this question, because this is a problem you could have done back in Calc 2. The formula for the arc length of a curve back in Calc 2 was integrate from t1 to t2 of the square root of dx dt squared. I wish I had a stylus. Okay, swag, you're getting kicked. See ya. Gonna ruin this for everybody. See ya. Get the fuck out. Booted. He's just gonna refresh and come back. That's the fucking annoying thing. He's just gonna refresh and come back. I fucking hate it. Yes, he's already back. I'm pissed. Plus dy dt squared. I'll play that game all night though. I'll keep kicking him out. Alright, dx dt squared plus dy dt squared dt. So, does this simplify? Yes, it does. We get L equals, for our function, what we're going to do is we're going to use the parameterization. Let's do it in green. X equals t. Y equals, what was it? 1 over a, is it a times something? A cosh x, a cosh t over a. Thanks, Andres. All right, so we're going to use that parameterization. Our bounds for t go from 0 to what? 0 to b, I think. Thank you. All right, so we're going to do 0 to b. The derivative of x with respect to t is 1. The derivative of, what is the derivative of y with respect to t? dy dt will be sinh of t over a. So this is going to be sinh squared of t over a. I should probably say sinh. I did use the chain rule. No problem. So, oops, whoa. Okay. Damn it. All right, so now let's clean this up. I'm gonna move this, scoot this up a little bit. Get rid of this. Let's get rid of this. Move this up. 1 plus sinh squared is actually cosh squared, and the square root of that would be cosh. So this boils down to integral of cosh t over a. The integral of cosh is equal to sinh of t over a, but we have to do the reverse chain rule, so an extra factor of a pops out like that. So for those of you who are a little bit lost, because I kind of went a little quick, the derivative of cosh is, a times cosh of t over a is sinh of t over a squared is sinh squared of t over a, plus 1 is cosh squared, the square root of which is cosh. That's why I get just that. The integral of cosh of t over a is a sinh of t over a. So does this go to 1 over a, not 1 over a, it goes to a times sine of, Eddie Gomez? Eddie, what's up, man? Welcome to the room. Hi, Eddie. No, it's going to be a times hyperbolic sine of t over a. Because when we basically, let's put it this way, if I'm integrating cosh of t over a, it becomes sinh of t over a, and I divide by 1 over a. But to divide by 1 over a flips it and gives me a times sine of hyperbolic sine of t over a. Cool? So plug in b, plug in 0, find the difference. And then when we do so, this gives me a hyperbolic sine of b over a. When you plug in 0, that gives you 0. So this is my answer. Now, my answer, granted, my answer doesn't look anything like hers. So what is her answer? It's something like square root of h squared minus a squared, right? Gotcha. Well, I don't know exactly what I would do to a hyperbolic sine of b over a. That should be hyperbolic sine. I don't know what I should do to a hyperbolic sine of b over a to get the same thing. I do. I fixed it. But I would leave it at that. That's fine. I don't think you'd be marked wrong for that. Yes, hyperbolic sine of 0 is 0. Yes. Hyperbolic cosine of 0 is 1. Kind of like the regular cosine and sine. Cool. All right, moving on to problem number. Ben and Kristen are just so nice. They just keep thanking each other, or thanking me, or thanking somebody. Problem 10. This is one give me a pain. This has been a pain in my ass. So problem 10. Actually, problem 10. I'm going to post on the wall. I haven't worked on it yet. Somebody go ahead and post and say, "Hey Andrew, can you do problem number 10 for me?" And I'm gonna work that one out. I don't want to work that one out here. I can come back to it at the end, but I'd rather not because it's giving me a headache, or at least I'd rather not do it on the spot. That's the only one that's giving me trouble this entire way through, so I'm going to skip it for right now. Problem 11, find the mass of the asteroid x to the 2/3 plus y to the 2/3 equals 1 with linear mass density sigma xy equals 1. Okay, so they said linear mass density. They said linear mass density. So because it says linear mass density, that should imply that we're doing how many integrals? Yes, one integral. Single integral. Linear mass density of, the mass density is 1. Of the asteroid x to the 2/3 plus y to the 2/3 equals 1. Apparently we want to do it all the way around, so ds. And we're going to say we need to parameterize this asteroid. So how might you parameterize x to the 2/3 plus y to the 2/3 equals 1? A lot of you are tempted to use r cosine cubed, r sine cubed. But you should only be using cosine cubed theta, y equals, or let's use t, I don't want to use theta. Y equals sine cubed theta. Let's talk about y. And again, it's important that you realize why you want to use only one variable here. You're not going to use an r. Yeah, exactly. Swag got it right. I'm only doing one variable here. There's only one integral, so I shouldn't have an r and a theta. A lot of people think that there needs to be an r, and it's true. There's sometimes you think, okay, polar coordinates, or anytime I'm using a cosine, I need an r cosine, I need an r sine theta. So that's two variables, right? But because we're doing a single integral, I should be using only one variable. So that makes me think, okay, it must be the case that my r is fixed, and it is indeed to be fixed at r equals 1. Cool? All right, so if I use x equals cosine cubed t and y equals sine cubed t, this gives me 1 ds. If I find ds is going to be the square root of 3 cosine squared. Oh, fuck. It's going to be 9 cosine to the 4th t sine squared t plus, this is if you do your dx dt squared plus dy dt squared, etc. 9 sine squared t cosine squared t dt. Okay, it looks like a mess, but trust me, it's going to boil down to something that's really simple. I can factor out the 9. I can also factor out a sine squared cosine squared, and when I do so, I'm left with 3 cosine t sine t. The inside of the radical is square root of sine squared plus cosine squared. So really, that's just going to be 1. That cancels and goes away and just becomes 1. Cool? All right, we're not going to chat anymore. Just to get people to shut up for a little bit. All right, so yeah, didn't think I could do that, did you? Can't say anything because it's fucking quiet now. It's fucking quiet time. I'm the fucking showstopper. Let's finish this problem and then I'll give the floor back to you guys. All right. So integral, I can't fucking stand all the fucking links and all the different colors. It looks like a MySpace. It drives me insane. All that shit's blinking in my eyes. Let me finish this problem. After that, I'm gonna take like a 2-minute break and then I'll give you the chat back. So give me a second. Now everyone's spamming the hand button, raise your hand. Cool. That's gonna drive me insane too. Great. Yep, here it comes. As soon as I mention it, the fucking people are spamming it. Super. Swag, you're gonna get booted. English major, you're gonna get booted. Or I guess it's not you, it's Kazakh State University. Fucking gonna kick him. Seriously. 3 cosine t sine t. I'm When I integrate this guy, it's going to give me 3/2 sine squared t. And I evaluate from, be careful, actually, yeah, you can do 0 to 2, oh no. Don't do 0 to 2 pi here. You might be tempted to do 0 to 2 pi, but guess what this gives you? I would love to hear your answer. Actually, do I want to give the chat back? I know you're all saying, yes, give the chat back. And I'm thinking to myself, no, it's a horrible idea. Yeah, no, see, I'm really conflicted. No, we're not going to give the chat back. Not just yet. You can do 0 to 2 pi, but guess what's going to give you? It's going to give you 0. Sine of 2 pi is 0. Sine of 0 is 0. So it's fucking useless. There's no point in doing that. So what you're supposed to do instead is integrate from 0 to pi over 2. Sine of pi over 2 is 1. Sine of 0 is 0. 3 over 2 is 3/2. But then we multiply by 4 to get the area of the total mass in all 4 quadrants. So that's going to give us an area of 6. I don't think I've messed anything up there, but let me double check. This is problem 11, I think. 11, the answer is 6. We're good. Okay. Any questions on that one? Oh, you want to ask a question? You can't because there's no chat? Okay, here it is. Now everyone's going to fucking say something. Here it comes. All right. I did not skip the Jacobian. Andres, I did pi over 2. I fucking literally just said, because 2 pi, the upper bound, is going to give me 0. So I just do 0 to pi over 2 and multiply by 4. Can I go over the factoring of the ds? No, I'm not going to. Again, we just had to realize that. No. How did I get 3's? I just integrated. The integral of 3 cosine t is 3/2 sine squared t. When you factored out the sine squared t, how? There was only a sine squared t on the radical. You took out a sine. There's still a sine squared. Okay, couple things. I did not skip a Jacobian. There's no Jacobian here. There's no Jacobian. There is no Jacobian whatsoever. This is ds. This is a conversion from ds to dt. There's no Jacobian. This is ds, and it's a very massive thing, I know. dx dt was what? 3 cosine squared sine t. When I square it, I get 9 cosine to the 4th t sine squared t. The derivative of, oh, yes, I can see why some people were confused. This should be a sine to the 4th. That was all. It's just a typo. So it should be a sine to the 4th, and that's a sine. So I guess that was Ali. That answers your question. Okay, there's no Jacobian here. This is just a conversion from ds to dt. Pretty big. You can factor out the 9. You can factor out a sine squared and a cosine squared. And when you do so, you're left with a sine squared plus cosine squared t. So this goes away. It's just going to be 1. And I'm left with this, 3 cosine t sine t. The integral of which you can do with a u sub, but I think I can trust you guys know how to do a u sub. The integral of 3 cosine t sine t would be 3/2 sine squared. Okay. Pull out cosine squared and sine squared. If you just speech, how'd you get the integral with the 9s? What 9s? Oh, how do I find ds? Okay, how do I find ds? I'm going to write this down. Just how do I find ds? ds. I feel like this is in my packet. Is this in my packet? Did I put this in my packet? Good. So I thought so. I did this like 10 times. Okay. All right, ds equals square root of dx dt squared. Now, it'll be different for polar, and this is what problem 10 is giving me a headache about because the parametric is easy. It's the one I give you, but polar is a bit different, and I've actually written it on the wall a few times. Cool? All right, so that's why I get this integral. Are there any other questions from people who actually taking me seriously right now? Because I'm a little worked up. It's just the lack of sleep. So I'm not actually mad at you guys. I'm just mad at the fact that I've been up since 8 and out of meetings at Study Edge and reviews. So, yes, Ben, it is 3/2, but we quadruple that because we want all 4 quadrants, so that gives us 6. So the reason we use cosine cubed is cancel out to 2/3 exponent. Yes, correct. Andres, correct. Or did you? No, we didn't do 10. I skipped number 10. Eddie, I didn't see your question. Let me scroll back up. I missed it. Good to know. Could we use usub? To what? To integrate 3 cosine t sine t? Yes, you could. If you wanted to integrate 3 sine t cosine t, you could use a usub to do that. Good? All right, those are all the questions I'm taking on that one. You can ask, again, more questions later, but I'm going to move on to number 12. Number 12 is a question I did in a video, so I'm not doing that one. Number 12, I did that in the video. So for those of you who are wondering about number 12, you can also get the solution to problem number 6 as well. Cool? And one token video. Have a gander. Problem 13, determine the mass of the triangular plate whose vertices are 1, 0, 0, 0, 2, 0, 0, 0, 2 if the mass density sigma xyz equals xy. Okay, a couple things you got to write down for this guy. Oh, I'm going to take a break. So, give me 5 minutes. I'm going to grab some orange juice and just 2 minutes. I'll be right back. Multiple attendees are typing. I'm going to drag the chat away, so be right back. No pulp. No pulp. No screwdriver either. No alcohol involved. Sorry I had to do these at such a late time, guys. I didn't realize that Calc 2 review was going to be rescheduled. So that's why it had to be moved kind of last second. Thanks, guys. It is, the kind of OJ is Tropicana, I think. Calcium, no pulp. It's with the blue label, the blue tops. It tastes good. Tastes good, man. Tastes good.jpg. Not mango flavored. I think my roommate's got that, actually. Yeah, I need my vitamins. I was sick. I played dodgeball. I play dodgeball on Saturdays, and when you haven't played dodgeball in 6 months, you get really fucking sore. The reason I haven't played in 6 months, the reason we played dodgeball, we had a hiatus of 6 months is because college football season takes over, and we usually play at 5 p.m. And 5 p.m. at least in the winter, 5 p.m. the sun's up for like 5 more minutes at 5 p.m. So you can't play. So we got the hour back, so I started playing dodgeball again, and I was sore all over. And then I was a little sick, and I got even sicker. I don't know, from eating something, or I had a little bit of a cough. And the worst thing is, I used to play Fridays, Brandon, but I think we moved it to Saturdays. So yeah, we could all play dodgeball. You guys are invited. I mean, I'll let you guys know when the next dodgeball game is. Shit. And so you guys are welcome to show up. If you guys know where West Side Park is, it's just like on 34th and 8th. And I was a little sick and I was a little sore, and I basically didn't eat anything on Sunday. I had fever, chills, lack of appetite, and fatigue, and I was just like crawled in bed and bitched and moaned, and that's why I didn't answer any of your wall posts on Sunday. I just like couldn't move. I was like being a little. I thought I was like, okay, well, this is it. This is how I die. So this is why I'm trying to refuel on vitamins and OJ. Yeah, some people actually do drunken dodgeball. Some people actually bring OJ and vodka and they get drunk and play dodgeball. So yeah, if you guys want to play dodgeball, feel free to come out. We do have balls or spheres, if you will. But yeah, I'll let you guys know when we play if you guys are actually interested in playing. Zach won't be there, no. Like I said, dodgeball we play at West Side Park. But I'll let you guys know if you guys. I will literally post in the Calc 3 wall where when I play dodgeball. Nope, no minimum height or weight. Girls are welcome too. So if Allie, you want to get out there and throw a ball, or Alex, you guys want to throw a ball around, whatever. Nicole, go nuts, throw a dodgeball and hit somebody in the face. Hit me in the face, go nuts. All right, so moving on to the next problem. Cool. Problem 13. Determine the mass of the triangular plate whose vertices are 1, 0, 0, 0, 2, 0, 0, 0, 2 if the mass density is sigma equals xy. All right, so for this problem, first of all, am I doing a single, double, or triple integral? A lot of people are saying double integral, and it's good you're saying double. The reason you should be saying double is because you realize, yes, the word plate. Yeah, it's good. I think you're integrate too, Kristen. I think you guys are all integrate. Double integral because the word plate is being used here, so plate means a double integral. We want to find the equation of the plane that passes through these points. That would be 2x plus y plus z equals 2. Now this is where I'm already going to get a lot of questions. Andrew, how do you know the equation of the plane is 2x plus y plus z equals 2? Beyond, I just know. I don't know what else to say. Can anyone still hear me? Good. Yes, Andres, use the intercepts to find the equation. It's just a little bit of intuition. 2x plus y plus z equals 2. You could do it the long way and find two vectors, take their cross product to make the equation of the plane. That seems to take some time to do. But if she gives you the x, y, and z intercepts, that kind of really gives away what the this is going to be. At least, I don't know what else to tell you. Just get some practice with it. If you want me to come up with some practice problems of how to make the equation of a plane given the intercepts, I'd be glad to do that. But right now, I can't think of a method off the top of my head to make it kind of clear why that would be the equation of the plane. Just make sure that when you plug in the intercepts, 1, 0, 0, 0, 2, 0, and 0, 0, 2, that it satisfies this equation. That's all I really can say about that. All right, so we're going to use that. Let's solve that for z. So we have z equals 2 minus 2x minus y. If we're going to parameterize the surface of that plane, we're going to use x equals u, y equals v, and z equals 2 minus 2u minus v. So, okay, I'm dying a little bit. So, here's this equation. Here's the plane. Let's draw some different color. We want to find the projection of the plane into the xy plane, or the uv plane, so to speak. So that would be z equals 2 minus, that would be v equals 2 minus 2u. Yes, we found the parameters. Now we're finding the integration bounds, Eddie. So the bounds for v, if I were to draw a line parallel to the v-axis or the y-axis, what would I hit first? I would hit v equals 0. As I pass through the region, I hit the line v equals 2 minus 2u. My lower bound for u is 0. The leftmost value for u is equal to 0. What value of u causes 2 minus 2u to be 0? That would be u equals 1. Cool? So those are my bounds for my integral. 0 to 1. Wonderful. Great. All right, now. Freddie Adu isn't actually a person in his class. That's like a celebrity or like a soccer player, right? Who the fuck is Freddie Adu? I have to check this out because I recognize the name. I feel like I should know who that is. Yeah, okay. That's what I thought. All right. So, got our bounds. We're doing the integral of if we're trying to find the mass of the plate, we need to integrate our density functions. So here's sigma, but our sigma is x times y. So here's x times y, but really x and y are u and v. So really I should say u times v. This is our sigma. So step 1 is kind of done. Step 1 was find the parameterization. Step 2 is, step 2 is actually do what? Step 2 is compute RU cross RV. It's not a fucking Jacobian. If she calls it a Jacobian, then it is. But is that what she calls it? Does she call it a Jacobian? Because she didn't call it a Jacobian last semester. Okay, I should never have tried to call it a Jacobian. Yes, it's like a Jacobian. What should we call it instead? I have no idea. What should we call me? What should we call the Jacobian? Okay, I have no idea. We'll call it a Jacobian. Fuck, who cares? It's just like a faux Jacobian. Here we go. Oh, faux Jacobian? Perfect. I like this. Faux Jacobian? We're going to call it a Facobian. I like that. Facobian? Phobian? I have no idea. Facobian? Probably not. Anyway. Okay, listen. Kim Jong-un. When do we get an equation for the plan? Long way needs to be in simplest form, right? Fuck off. RU cross RV equals. We got to find this determinant. IJK. The English major asks, when do we need to compute this? We need to compute this when we're doing a surface integral. All right? This is a surface integral, so we need to compute this Facobian. I'm answering that question right now, Will. Chill out. So, what is the derivative of x with respect to u? That would be 1. The derivative of y with respect to u would be 0. The derivative of z with respect to u would be negative 2. The derivative with respect to v of all these other guys would be 0, 1, negative 1. And to answer your question, Kim Jong-un, do you have to put it in simplest form? I don't think so. Just solve for z. So say z equals a number. Z equals some function. You shouldn't have 2z equals something. It should just be z equals something. All right, so this cross product will be, I think it's going to be 2i plus, I kind of told you what was going to happen here, 1j plus k, the magnitude of which is square root of 6. No, square root of 6. So, we're going to have times square root of 6. English major, you say, when do we do ds? You mean, there's ds and there's ds. Lowercase s usually is reserved for line integrals. Uppercase s is reserved for surfaces. Nick, you can do that, but I prefer to do it the way I'm doing it because it's consistent. I don't have to use 2 different formulas. I'm not memorizing 2 different dumb formulas. The square root of 1 plus z prime sub x, z prime sub y. I'm just doing RU cross RV every single time, and I'm just being consistent. I'd rather not learn 2 different formulas for RU cross RV. So for this problem, it's square root of 6. Cool? Now plugging that into so this is now square root of 6 du dv. At this point, evaluate your double integral, and you're done. That's it. Evaluate that double integral, and that should give you your answer. Yes, good point. Thank you, Bradley. It should be dv du. Thank you. dv du. Hendrik says, why are the bounds 0 to 1? If I told you v equals 2 minus 2u, for what value of u is 2 minus 2u equal to 0? You would tell me u equals? Swag, not quite. 1. Yes, u equals 1. Juan. Good? Is this really Jack? Did somebody change? I have no idea if this is Jack. Let's put it this way. Jack, what bar were you at with me last week? If this is really Jack. If you're really Jack, you'll get it right. But if you're wrong, if you're not Jack, you'll guess, and you might guess right. Dan, wait, why the fuck? Wait, no, Jack, you're wrong. This is not the real Jack. Jack's a liar. This is not the real Jack Thomas. It was Salty Dog. So Thomas was right, which is weird. Okay. He's not getting the boot. Give him the boot. No. All right. All right, so does anyone need me to compute this integral? RU cross RV, you guys, okay, not doing the integral. Cool. RU cross RV, I'm not going to do it again. You can ask on the wall. Just, look, RU cross RV. IJK across the top. Partial derivative with respect to U and V gets 1, 0, -2, 0, 1, -1. Cool? We're done. Done with this question. Let's see what's going on here. Why when changing the t to why is it always 0 to 1? When changing to t the bound, I don't know what you have to repeat that question. You've seen the function. It was already Andres. It was already on the page. It was on the page. Right? It was right there. There's the function z, right there. It's parameterization right there. Ah, good point. Yeah, I see what you're saying. I see what you're saying there, Kim Jong Un. Yeah, you probably should. That's a good idea. Shouldn't change. That's a good idea. Good point. Yeah. What was the v equals 2 minus 2u for? That was our upper bound. That's right here. Allie, to answer your question, v equals 2 minus 2u. I need that to figure out for my upper bound. Okay, going on. Next question. We're done. We're done. If you have any more questions, ask them on the wall. Moving on. 14. Find the moment of inertia about the z-axis. Okay. I tried doing this in lots of different ways. And you know what? I actually want to hold... I don't want to fucking tell you I'm going to skip because I'm going to sound like a bitch. I'm bailing. Let me work on this really quickly. Nothing about this problem suggests to me that this should be using a single integral, a double integral, or a triple integral. Because it says moment of inertia about the z-axis of the part of the homogeneous paraboloid z equals 1 minus x squared minus y squared that lies above the xy plane. It doesn't tell me whether or not I should be doing... It doesn't say it's a plate. It doesn't say volume. It doesn't say... The word part seems to me to make it... The word part makes me think it's supposed to be... The word part makes me think it's supposed to be a two-dimensional integral, but I got the wrong answer. To be sure, her answer is 25 root 5 minus 1, or it contains some sort of variant of that, like times a pi k. I don't care about the pi k, whatever shit. Is this part of her answer? 25 root 5 minus 1? The 25 root 5 minus 1? Okay, well, if that's the case, I'm going to try a triple integral, because doing a double integral didn't work. No, inertia's not always... Alex, did you watch my video about question 6 and question 12 on this review? Alexandra? If you watch it, you'll see that it's not. The answer is no. Okay. Okay, so you guys think it's a solid? Perfect. Let's do it as a solid. So, triple integral about the z-axis. So this is the... For those of you who haven't watched my video about the... questions 6 and question 12, this might not make as much sense to you, but the moment of inertia about the z-axis requires that we immediately start with x squared plus y squared. If you're looking for the moment of inertia about the y-axis, you use x squared plus z squared. If you're looking for the moment of inertia about the x-axis, you start with y squared plus z squared. And then you multiply by a sigma, and then dv or ds or whatever differential your integral requires. Cool? Thank you, Thomas. Might use it if needed. All right. I'm going to try and stop at 1:30, so I'm going to try and move these a little bit faster. We're told it's a homogeneous paraboloid, so what we can say is that sigma equals 1. So this guy can be replaced by 1, or k, I guess. We say k or times 1. So we have triple integral of x squared plus y squared. Now, what coordinate system should we use? We're looking at paraboloid. It doesn't say any. It's x. We see 1 minus x squared minus y squared. I'm thinking cylindrical coordinates or polar. Cylindrical. You should say cylindrical because this is 3 integral. So it's triple integral. We should say cylindrical coordinates. Cool. So we have triple integral of r squared times k times r dz dr d theta. Okay. For a paraboloid, my bounds for z, let's actually get a sketch of the paraboloid. Paraboloid looks like this. As we draw a ray parallel to the... By the way, I'm just curious, how are my drawings? Are they pretty good? Are they all right? Has anybody ever looked at my drawings before and thought, what the fuck is he doing? And then at some point later in the semester, they go, oh, that's what he's drawing. Good, well, I'm glad. Just curious. Draw a hypercube, can't do it. All right, so we draw a line parallel to the z-axis. What do we hit first? We hit 0. I like the taco one. Nick says, where's the density function? It's right there. Right there, bro. Homogeneous. So, 0 to the paraboloid z equals 1 minus x squared minus y squared is the same thing as z equals 1 minus r squared. So, 1 minus r squared, that goes there. My bounds for r would be 0 to 1. My bounds for theta would be 0 to 2 pi. And I think that would be it, but for whatever reason, I don't think that's the answer. That doesn't give me the answer. Again, for what value of r would 1 minus r squared equal 0? Good? Again, if you do this problem out, I don't think you get 25 root 5 minus 1, any sort of that shit in this answer. So I don't understand why this isn't the right answer. So you've got me. Thomas said he sent me something. It hasn't arrived in my inbox yet, so I'll give it a shot sometime later. But I have no idea why I'm not getting the answer. Clearly, it's not how you do it because it's not working. X squared plus y squared, yes. Yeah, that's what I did, Nicole, but it still didn't. It was close, but still not the right answer. So I don't know. I'm just gonna come back. Don't write any of this down. Just erase that bullshit because it was wrong. Like I said, I don't know. I'm gonna come back to it. I'll try it later. We're gonna move on to 15. So right now I'm kind of not. Let's see. Problems number 10 and 14 I have to show you on the wall sometime later. 15. Evaluate the surface integral. Square root of x squared plus y squared ds, where s is the sphere, x squared plus y squared plus z squared equals a squared. Okay, so it's a surface integral. Step 1, parameterize. How do I parameterize a sphere? If I want to be on the surface of the sphere, I have to fix what? Yes, fix rho. So x equals... what is this? Radius A, radius R, radius 4. I always forget what tab it's in. Radius A. So, x equals A cosine theta sine phi. Y equals A sine phi sine theta sine phi. C equals A cosine phi. Now, for this problem, I want to be... S is the entire sphere. They don't say between the cone or anything shit like that. They just say the entire sphere. So guess what? Theta goes from 0 to 2 pi. Phi goes from 0 to pi. The entire sphere. There's no restriction here. Cool? All right, so now, the next thing is, step 1's done. Step 2. Step 2 is RU cross RV. I gave you a formula for this, so use it. The formula for a sphere, RU cross RV, is rho squared sine phi, so it's going to be a squared sine phi. Step 2 is done. You don't have to compute that massive determinant and blow your brains out because that's a huge determinant. It takes a long time to do. Cool? All right. So now, that's step 1. Step 2, rather. Step 3 is sub in. So we're doing square root of, if you plug in x equals a cosine theta sine phi and a sine theta sine phi in for x squared plus y squared and then take the square root, that gives you just a sine phi. this is what the square root of x squared plus y squared comes out to be. I know a lot of you probably didn't want to plug it in, but you actually have to plug it in and give it a shot. Plug in x squared plus y squared, plug in these formulas here in for x and for y, and when you do so, you get a sine phi. It's actually pretty tame compared to what some other things we've seen before. A squared sine phi, d phi d theta. Oh, I need to make this a double integral. Hold on. This is a double integral 0 to pi, 0 to 2 pi. And this integral, I trust you know how to compute. All right, now I'm taking questions. Just to be clear, does the RU cross RV change the calculation from volume to surface area? What? Don't worry about it. We can have a discussion as to theoretically, what exactly does a surface integral do? Yes, well, a surface integral, we're not going to have that discussion. Just don't try and think about it. Just instead, you're kind of right. You're on the right track, David. Maybe the answer is yes. It probably takes a little more tweaking of your explanation than that, but you're probably right. But I'd rather not delve too much into that. Real fast. Why does 0 to pi were the row limits? Okay, those aren't row limits. Those are phi limits. There are no row limits. Row is fixed. The reason phi goes from 0 to pi is because it's the entire sphere. It doesn't say between the cone. It doesn't say less than this cone. It doesn't say between two cones. It just says the sphere. So it's the entire sphere. I'm not doing the ballerina thing. I'm not doing the pirouette. I could, but I'm not on camera, so wouldn't matter. How do I know to use spherical coordinates? What region do they want me to parameterize over? What shape? They tell me that S is the what? I think the fact that they say S is the sphere is usually my dead giveaway that I should use spherical coordinates. No more questions on that one. Moving on to problem, 16. Describe the flow lines of the vector fields F equals negative y comma 4x. Okay, let me... Just plot some vectors. So when you plot 1, 1, what vector do you get when you plug in 1, 1 for that vector field? Negative 1 comma 4. So when you plug, this is number, everyone's like, what number is this one? What number? It's what's right after the one we just did. So it's number 16. This is number 16. If you plug in 1 comma 1 in for the vector field given by negative y comma 4x, you get the vector negative 1, 4. The vector at the point 1, 1 should be drawn then as negative 1, 4. That vector looks like this. It's a bit steeper than it is. A bit steeper, and it's basically pointing at negative 1, 4. Plot the vector negative 1, negative 1. That vector looks like this. Plot the vector at negative 1, 1. This vector looks like this. Plot the vector at this point. This looks like this. If you had to guess as to what kind of shape this gives rise to, if you were to play the connect the vector game, you can actually plot this vector too. Plot this vector. I mean, plot a few vectors and see what ends up happening. Plot this vector, and we get. Let's do it with a green curve. We get ellipses. I don't know exactly. So to answer your question, Swag, are the arrows flow lines? I don't think so. I think those are just vectors of the vector field. I think the flow lines are curves that I guess. I thought flow lines were the vector fields because I don't know what the fuck she's talking about sometimes. I thought flow lines were just little individual vectors that you draw, but I think if what you should do is play the connect the vector game. So that's what I'm doing here. Is I'm playing the game connect the vectors, and when I do so, I'm getting these ellipses. If I drew some vectors out here, I would get this vector. I would get this vector. Get this vector. The flow lines are what happens when you see what pattern arises. If you were to drop think of this as like a whirlpool in like of water, and if you were to drop a leaf in that, you would see it circle around in a flow. Yeah, exactly. Cool. And then put arrows around to show direction. Exactly. Yep. Cool. We're gonna move on. We're not gonna do part B. Graph the flow lines indicating orientation. Plot the vector field that several chosen points. That's how you kind of figure out what the flow lines are going to be. Move on to problem 17. Problem 17 says consider f equals del u, or gradient vector of u, where u is equal to ln of x squared plus y squared to the negative 1/2. She usually uses u for the potential function. I used lowercase f, but she uses capital U. Doesn't matter whether you use capital U or if you use F, whatever. That email just came in from Thomas, so let me have a look. I'm going to look at number 14 really quick. Just give me a sec. That's what I did, but I didn't get the fucking same answer, so what the fuck? Alright, maybe I must have made a mistake in that problem, but we'll go back to 14 in a minute. Alright, so problem 17. What are equal potential curves? Equal potential curves are the set of points, basically are like level curves. So the question is, when is ln of x squared plus y squared to the negative 1/2? What did we do for level curves back in like exam 2? We said we're going to set the function equal not to 0, we're going to set it equal to k. Or I guess she actually uses c. Right? At which point you can stop there. Yes, this is problem 17. But she says, well, I can probably say I can bring the negative 1/2 down to negative 1/2 here, so I have ln of x squared plus y squared equals c. I can multiply through by a factor of negative 2. This gives me ln of x squared. Zachary, you're exactly right. ln of x squared plus y squared equals c. Now you might be wondering, well, Andrew, you just multiplied through by negative 2. Shouldn't you have a negative 2c? Yeah, but listen up. I don't have a negative 2c because negative 2 times a constant is just another constant. So I don't say negative 2c, I just say c again. In much the same way, I'm going to do e to both sides. I'm going to exponentiate both sides. I'm going to do e to this side, e to this side. E to the ln makes this x squared plus y squared. E to the c is just, again, another constant. So I'm going to say c, and this is why her answer for the equal potential curves is x squared plus y squared equals c. Cool? David B, that's actually a really good way of putting it. I think like directionalized contour lines. It's actually not a bad way of putting it. All right, so that's part A. We're going to move on to part B. Part B says find and graph the flow lines. I'm not going to do that. But the flow lines would just be, as David B said, directionalized contour lines, I guess. Oh, wait, no, never mind. Those are... you can draw the vector field. Oh. Here's what you're supposed to do. So we just established that x squared plus y squared equals c were the equal potential curves. Okay? We just established that x squared plus y squared are the equal potential curves. So those would be circles centered at the origin like this. These are all equal potential curves. So every point on the blue circle has the same potential. Every point on the green circle has the same potential. Every point on the red circle has the same potential. Listen to this. Listen. I'm going to type it too just because I think it's that important. Flow lines are perpendicular to the equal potential curves. Flow lines are perpendicular to the equal potential curves. So, this flow line here, here's a flow line. Oh, fuck. Here's a flow line. Here's a flow line. All these lines are perpendicular to the equal potential curves. Good question. How do you know the direction? 1 second. They don't say it. Transfer doesn't say a direction. It's weird. Don't know. Couldn't tell you. I mean, you could draw here's what you do. You just plot a few vectors on your vector field. That's all you really do. Yeah, for 18 you need to know, but it doesn't tell you the flow lines. For problem 18, it tells you determine the oriented curves of steepest ascent of the function of u. It's a different question, though. The way you can do this is by looking at the vector field. So quickly, let's compute the vector field. I'm not going to have much room to do it, but I'm going to save you the time. Basically, find the derivative of negative 1/2 ln of x squared plus y squared with respect to x and with respect to y. When you do so, you get negative x over x squared plus y squared, comma, negative y over x squared plus y squared. That's the partial derivatives with respect to x and y. That's my vector field f. And negative x, negative y points toward the origin. So that's why you get, I'm assuming the flow lines would point toward the origin. Because that's my vector field. Again, my vector field is given by what I have bracketed over on the right. If you plot pick any point you want to, let's do 1, 1, and if you plug in 1, 1 into that vector field, you get negative 1/2, comma, negative 1/2. At 1, 1, and you go to plot 1, 1, you plot that vector, it points toward the origin. Yes, the vector field determines the direction of your flow lines. Yes. Any line that is perpendicular to the equal potential line. So if I had an offset center, it would be elsewhere, yes. Don't quadrant 2 and 4 lines point outward then? No, because these will also point to the center. You can try the point 1, comma, negative 1. Sure enough, that vector will give you negative 1, comma, 1. That vector points to the origin at that point. Will Mushim, yes, the vector field is the gradient. Yes, and if I plot 1, 1, that gives me this vector right here. Good? All right, we're done. I'm not going to spend too much time on this. I got like what I promised was 12 more minutes, but I'll stay longer if I have to. I don't want to spend too much time on this drawing shit. I can do more on the wall. Let's see. What are some good ones? Not going to do number 18. 19, let's see. Let's pick a few more questions. 19, 20. God, I don't want to do all of these. 19, 20, 23. I'm going to put this at the top. 19, 20, 23. 19, 20, 23. Shut up. Guess what? What you guys think doesn't matter to me. So 19, 20, 23, 20. Fuck. I'll talk a little bit about 25, but I'm not going to spend too much time on it. We're not doing 18. 18's, I just told you I'd do 17. 18 is not that bad. Those are equal potential surfaces, though, so not level curves or level surfaces. Don't spam, though. That's fucking rude. All right, we'll do those, and I'll try and I'll go longer if I can. So 19. Stop fucking spamming. What you think doesn't matter. All right, no spamming. 19. Django Fett says, "Boom. What you think doesn't matter." I like that phrase. What you think doesn't matter. Evaluate the work done by the force y squared, comma, x squared in a particle moving. This is a fucking good question. This is gonna come up tomorrow. None of you are gonna fucking know how to do it because you want to problem number 18. I need to know how to graph an equal potential surface. I'll be impressed if you know how to do number 19 correctly. If you got it right, well, congrats to you. But I feel like 19 fucked a lot of people up. So we're doing 19. 19. So it's the upper half of this ellipse. Like that. Upper half of the ellipse. Traverse clockwise. This is important because a lot of people traverse it normally. They let x equal a cosine t, and they let b equal, or they let y equal b sine t, and that's fucking wrong because it's going to traverse the upper half of the ellipse counterclockwise, but it says traverse it clockwise. Hello? I think my roommate just came home. Okay, so a cosine t, y equals b sine t. If you don't put a negative in front of the a cosine t, you get it fucking wrong. You get it wrong. So you put a negative here because if you don't, this negative makes it traverse clockwise as the question tells you to do. So you make sure you put this negative here, all right? Right, Zach said it. X equals negative a cosine t. So step 1, parameterize. It's almost done. We need to find our bounds for t. If you use the bounds for t 0 to pi, that will give you the bounds you want. So step 1's done. Step 2, sub in. So we're doing the integral of f dot dr. F is equal to y squared x squared. So that's going to be b squared sine squared t, comma, a squared cosine squared t. That's f. And you need to dot this with dr. So dotted with, let's move this down here. Dotted with dr. Hey, did they have like a stat test tonight? Is that what happened? Dotted with dr. The derivative of my parameterization is a sine t. The derivative of my parameterization with respect to t of y is b cosine t. So, listen, x. Will there ever be any situation where y equals negative b sine t? Have a guess as to how that happens, changes my curve. Just going to make it upside down, all right? So, all right, so f dot dr, when I compute this dot product, this gives me a b squared sine cubed t. It's not a vector field, so I don't need to put this anymore. Plus a squared b cosine cubed t dt. I'm evaluating from 0 to pi. And I will leave you to your own devices to do that integral. Cool? All right, any questions on that? Okay, so can you just add a negative at the end? Yes. Henrik asked a good question, so if you want to read that, you can. Why did you put y in the f and the x? Because all right, moving on to the next question. Number 19 is done. It's dead. Whoa. Number 20. Shit, where did my review go? Negative 20. There it is. The curve C is given by the parametric equations x equals t cosine t, y equals t sine t, z equals t. This looks very similar to a curve. What curve is this, by the way? T sine t, comma, t cosine t, comma. For those of you who weren't at study hours yesterday, what is this? Don't fuck. Okay, Ryan already knows. I'm assuming that some of people heard from me because they came to the actual regular study hours. Yes, this is a conical helix. The reason for this is it looks kind of like a helix, but the fact that there's an extra t as a coefficient of the sine and the cosine, this introduces a factor of, this introduces like a radial component outwards. So this is like a, someone actually said at study hours, picture a tornado. This is a conical helix. Yes, exactly. So picture a tornado. This is a conical helix. That's what the name of this curve is, conical helix. The question says, evaluate the line integral f dot dr where f of r equals r. This is what fuck people up to. What does f of r equals r be? What is f of r equals r? I don't understand what that means. I have no idea. Okay, f of r equals r just means this. That would be x, y, z. Yes, that is Andrew's nerd voice. I can explain, after this is over, I'll explain what Andrew's nerd, where that comes from, but make sure you remind me to tell you that story after this is all over. This is the nerd voice. Can you tell me why that f of r is equal to r? That's the nerd voice, but it's actually called the PH voice. But I'll tell you that story sometime later. Alright, so x comma y comma z, or x comma y. In this case, it's x comma y comma z because we're doing it's a conical helix and it's in 3 dimensions, so that's why. So the integral of f dot dr, well, replace x, y, and z by their respective. So step 1 is the parameterization is already given. Step 1's done. We don't have to do anything for step 1. The parameterization is given. X, y, and z I'm going to replace by t. Is it t cosine t? T sine t? Comma t. Dotted with the derivatives of our parameterization. Now taking the derivative here is going to be pretty. It's going to be like, fuck, I regret doing this problem so much. Cosine t minus t sine t, because you have to do the product rule, comma, the derivative of t sine t is going to be sine t plus cosine t, comma 1. Now when you do this dot product, here's what I end up getting. Let me see if I can move this around. This dot product gives me t squared, just t squared. I think it just gives me t squared. T squared cos, no. It's just t, 2t, yeah. This dot product, when you do this dot product out, it just gets 2t dt. The integral of 2t dt from 0 to 2 pi is t squared, plug in 2 pi, plug in 0. This gives you 4 pi squared. That's your answer. Cool? We're done with number 20. Problem 23. Vector field 2xy, x squared plus 2yz, comma y squared. You all should know, I'm not going to tell you how to do it, you all should know how to derive the, if the curl, first of all, the curl, you should know how to do curl. Curl of f equals 0. I'm not going to show you how to do curl, you should know how to find the curl of a vector field. The curl of this particular vector field for problem 23 is 0. If you find that the curl is 0, then you know that it has a potential function lowercase f, or in her case uppercase u. Something else I'm not going to tell you how to do in this review is how to find a potential function. You should know how to find a potential function, at least for one that's this simple. And if you do it for this one, I think the potential function you get is x squared y plus y squared z. Yes, it's that integral shit. So that's my potential function. So we've done parts A and parts B. The curl is 0. Step 1, check. Find the potential function. Step 2, check. What is the value of the integral of the vector field f along any closed piecewise smooth curve? Well, if you want to use the flowchart I gave you, this is where I say use the flowchart. The integral of f dot dr on a closed curve is 0 so long as f is conservative. So 23 is done. 25. I'm not going to do any of these, but I am going to tell you they all have potentials. They all have potential functions. You just need to find them. They're not that bad. I can actually tell them. I can recite them to you. Actually, I'll just write them down. The potential functions, and you should be able to find them on your own, but these are the potential functions for A, B, C, and D. I'm not going to do any of them. I'm just going to give you the potential functions. You should know how to find a potential function. No excuse if you don't know how. This is A. This is B. C is this one. This is going to be ln of xyz, I think. Let me double check that. No. I mean, I goofed. That one's D. And then C is just xyz. I'm telling you what the potential functions are. You should be able to find them on your own, and they actually aren't that bad. You should be able to find those. They're actually pretty easy to do. Okay, for those people, I keep hearing use flow lines are the direction of steepest ascent. Gradient vector points in the direction of steepest ascent, aka vector field points in the direction of the greatest ascent. Yes, Nicole, you plug in the upper bound, you plug in the lower bound, find the difference, and you're done. Good? Pup Levin, I'm just giving you all the potential functions for problem 25. You can find them on your own. I trust that you know how to do that. Okay, last one, problem 26. Show that the components of f have continuous partial derivatives in the domain E equals r squared slash 0, 0, 0. What all that means is the continuous partial derivatives are that if you say, I think the way you're supposed to show this is by doing partial part. I don't know if you should take the partial derivatives. I guess all you need to do here is realize that negative y over x squared plus y squared and negative x over x squared plus y squared, those partial derivatives, the derivatives of those will exist simply because at every point other than 0, 0, you won't end up dividing by 0. There's no divide by 0 error. Divide by 0 only happens at 0, 0. That's what I thought, Swag, is I thought these partials were already given, but maybe you should actually look at the partials, because in order to say that the integral over a closed loop or a closed curve for a conservative vector field is 0 is if the partials of your vector field. So you have to take partials of those. All right, part B. Show that curl of f equals 0 in E. Sure enough, the curl is equal to 0. You can do the computation, and when you take the partial derivative, you find that the curl is indeed 0. However, when you compute the line integral of f dot dr over C, you actually end up getting, you'd think that parts A and B, together with the fact that f is conservative, because we have curl of f equals 0, and C is a closed curve, you would think that f dot dr is 0, right? But the answer to part C is actually 2 pi. The answer to part C is 2 pi. So what the hell happened? Well, the thing is, I wanted you to believe that it was always true that f dot dr is equal to 0, but the only time it isn't true is if your partials of your vector field aren't continuous on any point that the curve encloses. Sure enough, the curve, the circle x squared plus y squared equals 1, or is it x squared plus y squared equals 25? Oh, just a unit circle. X squared plus y squared equals 1. That circle encapsulates the origin, over which the first order partials of your vector field don't exist. So you cannot apply the formula that I've given you here. This formula does not apply because the first order partials of your vector field don't exist at 0, 0. Yeah, sure. All right. So the last part says, is there any contradiction with parts A and B? No, there's no contradiction. Despite the fact that the curl of f is equal to 0, and despite the fact that it's a closed curve around a closed curve, it's a closed curve with a conservative vector field, we shouldn't expect to get 0 because our first order partials are not continuous at 0, 0. Part D says, what is the value of the integral f dot dr over a simple closed curve that does not enclose the origin? Well, any other simple closed curve that does not enclose the origin won't enclose 0, 0, and so we should expect the line integral of f dot dr over that closed curve to be 0. Good? How did I find 2 pi? Parameterize your curve. So x equals cosine t, y equals sine t. F equals, what was the vector field f? It's given to you. The vector field f is given to you, and if you do that, you get what? Negative sine t, comma cosine t. dr equals, turns out the same thing, negative sine t, cosine t. F dot dr, in that case, would be sine squared t plus cosine squared t equals 1. So you're doing the integral of 1 from 0 to 2 pi. It's all, remember, the reason it's 0 to 2 pi is it's all the way around the origin, all the way around the circle. The integral of 1 from 0 to 2 pi, 2 pi. Any other questions for me? I've got to bail. No, I can't. I can't. I am leaving in 2 minutes. Oh, pH voice. Yes, good question. So I've got 3 minutes left. I'm going to use it to explain the pH voice. So the pH voice is me talking like this, the pH voice. So back in high school, there was this kid who sat next to me in AP chemistry, and he always asked me for help on every single problem, every single day. And one day I got sick and tired of it, because if only he had paid attention for the first 15 minutes of class, where the teacher would just say, here's how you do this problem, and then he would give us some problems to do. If only that fucker would pay attention the first 15 minutes of class, he would then understand how to do the problem, and he wouldn't have to come bother me. Hey, Andrew, how do you do this problem? Hey, Andrew, how do you do this problem? Hey, Andrew, how do you do this problem? So one day, we were learning about, well, pH in chemistry, and the teacher goes on for 15 minutes. This is how you do this problem. You titrate, yada, yada, yada. When you titrate, this is what happens. Moles of HCl, yeah, I don't know. And I was like, okay, I get it. Lo and behold, without fail, the kid next to me says, hey, Andrew, how do you do the, can you help me with this? How do you do the pH, how do you do this pH problem? And I said to him, in the same exact thing that he said to me, but in the tone of voice that's as follows. Hey, Andrew, how do you do the pH problem that he's doing? And he got so pissed that I just retaliated at him with that voice, that he took all my papers on my desk and threw them on the floor, and then I was like, man, what the fuck? I guess I was really infuriating. Well, turns out whenever you use that voice to somebody, it really pisses them off. Whenever somebody says something nerdy, if you can do this especially at me, anytime I say something like, oh yeah, f is a conservative vector field over a closed region, so the integral line integral 0. You can repeat back to me, yeah, so f is a conservative vector field over a closed interval, so the line integral 0. And that would be infuriating, I guess, to somebody who doesn't like to be mocked like that. And that's where the pH voice came from. All right, see you guys. No problem. Bye. That's the pH voice. No problem. Thanks, guys. I am kicking you guys out in 30 seconds, so say bye. Post your questions.